Hello and welcome to MyScience Tutorials. This is the third and then the final part of our AC theory course or tutorial video. And then in this video we are going to look at circuit combination of an AC circuit. Now if you are now watching this AC theory video and this is the first one you are watching, I recommend you go and watch the part 1 and then the part 2 so that you can follow along with me as I go through the part 3 with you. So but then if you've watched the first and then the second one already, you are good to go with me, and then I believe we are all starting on the same page. Now in the second video we look at what a phasor diagram is, and then the types of circuit that we have, and then how we can get the reactance offered by either a capacitor or an inductor or a resistor. Now in this third part we are going to look at a combination of two or more of these components and see how we can get the overall opposition or the overall resistance that they offer, and then how we can use this resistance to calculate other variables such as current and then voltage. Okay, so let's have a look at the first type of circuit that we are going to treat in this tutorial. So the first one, we are going to look at the RC circuit. So the RC circuit is just for this is a resistor and then a capacitor. So we have a resistor and then a capacitor together in one AC circuit. So let's have the diagram. So we have the resistor over here, then a capacitor over here, and we have our current flowing in this direction, then we have our AC source over here. Now there is a voltage across the resistor, and then we have a voltage across the capacitor as well. Okay, now we need to know that what the current in this, okay, that the same current flows through this because they are in series, and then we know in series whether we have two resistors or three resistors in series, the same current flows through them. So that is a constant. Now the phasor diagram, okay, in the second video or the part 2 of this video, we look at what a phasor diagram is. Okay, now the phasor diagram of this particular circuit is given in this way. So we have over here, we have our VR over here, which is what I have over here, which is the voltage of the resistance, and then we have our VC lagging by an angle of what, 90 degrees over here. Okay, but then let's just remove that for now. Now this is VC, which is the capacitive voltage, and then we have the effective flow. This is VR, like I said, and then we have the current flowing in this way. Okay, so this, we have an angle over here. Now this is the phasor diagram, like I said, and then the alpha over here is what we call the phase angle. Now this is really interesting. Now we have a horizontal and then a vertical component. Okay, this is more like a vector. Okay, and this is the resultant reactance of this circuit. So it means for this entire circuit, okay, the overall opposition or the resistance they are offering to the flow of current is the one that we have over here, which I'm going to represent with V. Okay, so for us to get the value of V, we need to do some deductions. Okay, so using Pythagoras theorem, okay, we know the resultant square, which is the V square, will be what, the sum of the square of the two components we have over here. So we have our VR square plus what, our V6 square. Now this, we know our VR for resistance, the voltage of a resistor is equal to what, IR, so we square it, plus that of the capacitor is what, I times what, IXC square. So this is the capacitive reactance from the second tutorial if you've watched that. So from here all we need to do is what, is to simplify. So we have I square R square plus what, I square XC square. So V square is equal to what, if we factorize I square out, we have what, R square plus what, XC squared. Okay, So from here we know we divide all by like root, okay, of everything over here. So this cancels this. So we have voltage is equal to what? This will cancel this, so we have our current, and then multiplied by the root of what? R square plus what? XC square. Now if we divide voltage by current, or voltage by current, we get some sort of what? Resistance. Okay, now in this combination of two or more different components in an AC circuit, okay, the resistance that we offer over here is what we call the impedance, and then it is represented by Z. Okay, so if we divide both sides by what? I in this case, okay, so it means we divide here by I, we divide here by I, okay, then the voltage over the current over here will give us what? The impedance, which is Z. So the V over I over here will now become Z, will now be equal to what? Root of what? R square plus what? XC square. So this is how we calculate the overall resistance offered to the flow of current in a circuit containing what? A resistance and then a capacitor. So the Z is the impedance, and then the impedance is what? The total opposition offered to the flow of current in this particular instance. So the formula that we'll be using in calculation, in case we have a resistor connected in series with the capacitor and we want to find the overall resistance of the circuit, which is the impedance, it will be given to us by the square of the resistance plus the square of the capacitive reactance, and then we find the root of that, and that will give us the impedance. Now we also need to look at another thing. Now in case we are asked to find the phase angle, okay, in case we are asked to find the phase angle, which is like when I drew the Phasor diagram, okay, we have an angle over here, which was what I said was the phase angle. So in case we are to find the phase angle, okay, tan alpha, okay, is given to us by what? VC over what? VR, okay, which means our VC is what? IXC, and then our VR is what? IR. Now the current will both cancel out, so we have tan alpha, which is the phase angle, given to us by what? XC, which is the capacitive reactance, divided by the reactance of the circuit. So these two equations, this whole equation as equation number 1, and then this whole equation as equation number 2, they are really important when we are looking at an RC circuit. So if you are asked to find the phase angle, you use tan alpha is equal to what? The capacitive reactance divided by the resistance of the resistor. And then if you are asked to find the total opposition to the flow of current, which is the impedance, it is what? The root of what? R square plus what? The capacitive reactance square. So this is for the first example, which is what? An RC circuit. Now how do we find the impedance of other combinations? We are going to look at those ones as well. So let me get rid of everything. Okay, let me use white. All right, so the second type of circuit we are going to look at is when we have a resistor, okay, connected to an inductor. And then we have our current flowing here. We have our AC source, our AC source. Then we have a voltage VR across the resistor over here, and then we have VL across the inductor over here. Now in this example, okay, the phase diagram looks something like this, where we have the VI and then the VR over here. Now remember when we were in the second video, okay, we explained how come we have the Phasor diagram of the inductor leading, we have the voltage of the inductor leading that of the current in this way. Okay, we explained that. So this is how the Phasor diagram looks like if we have the combination of a resistor and then an inductor. Okay, and then we have an angle over here, which is the phase angle as well. And then the same way we have, this is our resultant flow of which is our V, which is the current, the voltage, sorry, in this particular instance. Now, just like the way we did for the first one, okay, using Pythagoras theorem, the V over here, okay, the V square will be equal to what? This part is VL, okay, so we have VL squared plus what? VR squared. Okay, so we have this will be equal to what? This is IXL squared plus what? IR squared. So from here we can say V square. If we simplify this, we are going to get I square into bracket XL plus what? R squared. They are all squared. Okay, so if we find the root of all of them, we are going to get V is equal to what? I root of what? XL squared plus what? R squared. And then if we divide both sides by the current, we get the impedance, which is what we are calling the total opposition to the flow of current if we have either a resistor or a capacitor or a resistor or an inductor. Okay, the overall resistance when we have this combination of components is what we call the impedance. Okay, so the impedance in this case will be what? The root of what? R square plus what? XL square. So this is the impedance in case we have this combination. It's just like the first example. And then the same way, if you are to find a phase angle for this particular example, we have tan alpha. Okay, tan alpha over here will be equal to what? Tan is 2, okay, so opposite over adjacent. So if I close this, okay, this is the opposite, okay, which is what? VL. The opposite is the VL over this is the adjacent. Okay, so we have what? VL over what? The adjacent, which is what? VR. So we have what? IXL divided by IR. So the I will cancel out, and then we have our tan alpha will be equal to what? The inductive reactance divided by the resistor. So this is how we find the impedance, and then we find the phase angle in case we have a combination of what? A resistor and then an inductor. Now let's quickly look at the third part. If we have a combination of all three, so we have a resistor, we have a capacitor, and then we have an inductor, how do we get our answer? So in case we have those three, let me be quick with that. So we have our circuit, we have our resistor, we have our inductor, and then we have our capacitor. Okay, so they all have a voltage across them. Let me make this sharp. So this is VL, this is VR, this is VC. So we have our current, we have our AC source over here. So now for this one, the Phasor diagram, sorry, looks like this. So we have our resultant voltage, then we have our phase angle over here. So we have our VR, okay, which is that of the resistor. But then on the vertical axis we have what? VL minus what? VC. This is VL minus VC. So if this is what we have for the Phasor diagram, just like we did for the first two, we have our resultant square will be equal to what? VR square plus, in this case we are subtracting the two of them, so it will be what? VL minus VC all squared. Okay, so we break this thing down. We have what? Our V squared to be equal to what? IR squared, okay, plus into bracket we have IXL minus what? IXC all squared. Okay, so if we divide, okay, if we expand this, we get V square is equal to what? I square R square plus in this case we will be getting we'll be getting I square outside bracket, then we have XL minus what? XC square. Okay, so if we divide both sides by what? I, okay, so we'll be having our voltage, we divide, no, so let's take it from here. Okay, we divide both sides by what? I square. Okay, so we divide by I square, so we'll be having this square divided by I square, and then plus this as well, XL XC all square divided by I square. So if we do that, we are going to get our impedance straight away from here, okay, because this will cancel out, and then we have our voltage over current, so which is the impedance will be given to us by what? The root of what? R square in this case, okay, because this cancels out this. Then we have R square plus into bracket XL, the capacitive reactance, minus what? The inductive reactance minus what? The capacitive reactance all squared. So this is how we find the total opposition to the flow of current in this particular circuit. And then if we are asked to find a phase angle, we know phase angle tan alpha will be equal to what? If we finish this diagram, okay, this will be what? VL minus VC, okay. So so we have opposite will be what? VL minus VC divided by what? VR, which is what we have over here. And then if we further break this down, we'll be getting what? XL minus what? XC divided by R. So we use this, okay, to find the phase angle in case we have this three combination, and then we use Z is equal to what? The root of R square plus this squared to get the total opposition to the flow of current in case we have these three combination. Now let's have a look. Let's try some few examples so that we can actually better understand all that we have done so far. So example number 1. So the question is asking us to, this is the circuit we have. We have to calculate the following from the RC circuit we have over here, okay, not above, yes, adjacent. So we have to find the reactance of the capacitor, okay. So the reactance of the capacitor means what? The capacitive reactance, okay. And we know XC is equal to what? 1 over 2 pi FC, okay. So from here we have what? 1 divided by 2 pi. The frequency we have over here is 25 Hertz, so we have 25, and then the capacitance we have over here is what? 10 microfarad, which is what? 10 times 10 raised to the power minus 6, okay. So if we input everything over here into the calculator, we are going to get 636.6 ohms. So this is for the first part, that is the reactance of the capacitor. So the II is the impedance of the circuit. Now because this is an RC circuit, okay, the impedance is equal to what? The root of what? R square plus what? XC square. So we have here root of what? The resistance is 100, so we have 100 square plus the XC is what we just calculated, so 636.6 square. Now the root should cover all of them. So if we punch this into the calculator, we have our impedance to be what? 644.4 ohms. So that does that for the second part. The III aspect, the current through the circuit. Now the current over here will be what? The root mean square voltage will be what? The root mean square current times the impedance, which is the total resistance in this circuit. So our current, which is the root mean square current, will be equal to what? The voltage, which is what? 90 volts, divided by the impedance, which is what? 644.4, okay. And then this will give us what? 0.14 amperes. And then the second to last, that is the voltage across the capacitor, that is, okay, this VC. Now the VC will be what? The root mean square current, okay, times the capacitive reactance, which is what? This, okay. So thank God we've already calculated the current, so we have 0.14 multiplied by the capacitive reactance that we calculated first, which is what? 636.6, okay. So if we punch this into the calculator, we have 89.1 volts, okay. So the final part is average power dissipated, okay. And we know power is what? Voltage, which is the root mean square voltage, times what? The root mean square current. So this is what? The root mean square voltage is what we have over here, which is 90, times what? The root mean square current is what? 0.14, and then we get what? 12.6 watts as our answer. So this is how we solve a question on an RC circuit. Let's have a look at another example. So example number 2. So example number 2, we have a 20 microhenry inductor is connected in series with a 50 ohm resistor. Now a 100 hertz alternating voltage source is connected across the combination. Given that the root mean square value of the voltage is 100 volts, calculate the potential difference across the resistor and then the inductor, and then the phase angle between the applied voltage and the current in the circuit. So let's write solution. Now let's try to draw the circuit so that we can actually envisage what we have in this question. So we are having an inductor which is connected to a 50 ohm resistor. So we have our resistor, it is 50 ohms, and we have our inductor. Then we have our AC source. We have our current here. So this is 20 millihenry, milli, not micro. So this is L, this is R. So we have our voltage is 100 volts. We have 100 volts over here. That is 100 volts, yeah, exactly. And then we have our frequency is also 100 hertz. Okay, so this is what we have, and then let's quickly solve this. Okay, so the first aspect of the question is telling us to find the potential difference across the resistor and the inductor. Now, so for us to find the potential difference across, then we need to get the capacitive reactance and then the resistance of this capacitor, which is what we already have. So for the first part, okay, for this first part, let's find XL, which is the capacitive the inductive reactance for this particular one. So this is what? 2 pi FL. So this is what? 2 pi. The frequency is what? 100. Okay, and then the L is what? 20 times 10 raised to the power minus 3. Okay, so the XL, the value for the XL over here, if we point this into the calculator, will give us what? 12.57 ohms. Now, if that is what we have, okay, from then the question is telling us the potential difference across the resistor and then the inductor. Okay, so we have 2 pi. We have the inductive reactance. Sorry, I don't know why I keep on mentioning the capacitive inductance. So we have the inductive reactance over here. So we just need to find the impedance, that is the total resistance offered by these two components. So the impedance in this case is the root of what? R squared plus what? XL squared. So we have the impedance is equal to what? The root of the resistance is what? 50 squared plus what? The capacitive the inductive reactance, sorry, is what we have over here, which is 12.57 all squared. Okay, so we have our impedance to be what? 51.6 ohms. So now that we have our impedance, we know voltage is what? IZ. Okay, so our current in this case will be what? The voltage, which is 100 divided by 51.6. This is 0.6. Okay, so our answer, the current will be what? 1.9 amperes. Okay, so this is the value of our current in this example. Now remember, the question is asking us to find what? The potential difference across the resistor and then the inductor. Okay, but we know before we can find the potential difference, which is the voltage, okay, is equal to IR, we need to find the current. So that is what we did by finding the current over here. So with that being done, let's now find let's now answer what the first part of the question is actually asking us to do. So the I across the resistor, okay, we have V is equal to IR. So we have our current, which is 1.9 times 50. Okay, so we have our 1.9 times 50, and then this will give us what? 90.7 volts. So we have the second one, VL is equal to what? 0.19 times the 12.57 we have over here. So this will give us 24 volts. Sorry, this is supposed to be 97, not 90.7. So this is 97 volts. Okay, so does that for the first part. And then the second part is telling us to find what? The phase angle. So we have tan alpha is equal to what? Because we have an inductor and then a resistor, we have our inductor at the top, so we have 12.57 divided by what? 50. Okay, so if alpha is equal to what? Tan inverse of everything we have over here will give us what? 14 degrees. Okay, so this is how we solve some few examples on the combination of two or more components in an AC circuit. So thank you so much for watching. I hope you enjoyed the full AC theory concept from tutorial 1 to tutorial 3. And then if you find it useful, kindly subscribe to our channel, gives us a thumbs up, and then comment in the section below so that we know how to improve upon our tutorials. Okay, so thank you so much for watching, and then I'll see you in the next video. Bye bye.